Take one step forward. From where you are standing, you do not have long left to live, and you will spend what remains in an eerie, almost peaceful calm. But to anyone watching from a safe distance, you never take that step at all. They see you slow. They see you redden. And they see you freeze at the edge, a smear of fading light, hanging there for the rest of time. Both versions are true. Welcome to the strangest object in the universe, where the question isn't only what happens when you fall in, it's whose version of events you believe. First, forget what the name suggests. A black hole is not a hole, and it is not made of nothing. It is the opposite. Too much something, crushed into far too little space. When a giant star runs out of fuel, gravity finally wins the war it has been fighting for millions of years. The core collapses, and matter is squeezed toward unimaginable density. What remains is a region where gravity is so intense that not even light, the fastest thing there is, you can climb back out. In 1916, a physicist named Carl Schwarzschild, working from the trenches of the First World War, solved Einstein's equations and found the exact size of that point of no return. We call it the event horizon. For our journey, ignore the small black holes left behind by single stars. Their gravity would kill you long before anything interesting happened. Instead, aim for a giant, a supermassive black hole, millions of times the mass of our sun, like Sagittarius A, the monster sleeping at the center of our galaxy. Because, and this is the first surprise, the bigger the black hole, the gentler the crossing. And so, you fall. At first, nothing seems wrong. The black hole announces itself not with darkness, but with light. Gas and dust spiral inward in a vast flattened whirlpool. The accretion disk, heated by friction to millions of degrees, glowing brighter than entire galaxies. This is how we find them. This is the glow the Event Horizon Telescope captured in 2019. Humanity's first photograph of a black hole's shadow. As you fall closer, the universe behind the black hole does not vanish. It bends. Light from stars directly behind is curved around the edge and delivered straight to your eyes, so the black sphere appears wrapped in a halo of smeared, distorted starlight, an Einstein ring. Closer still, you reach the photon sphere, where gravity is strong enough to bend light into a perfect circle. For one vertiginous moment, if you glance to the side, you might see the back of your own head. Light that left you, looped around the black hole, and returned. The familiar sky is gone. The entire cosmos is now crushed into a shrinking, brilliant ring above you. And below, there yawns a perfect, depthless black. Ahead lies the event horizon, the boundary Schwarzschild found, the surface of no return. Cross it, and to escape, you would have to travel faster than light. Nothing can. And here, the universe begins to tell two completely different stories about you. To a colleague watching from a safe ship, you never arrive. As you approach, your falling clock appears to tick slower and slower, stretched by gravitational time dilation. The light leaving you is dragged to longer wavelengths, red, then infrared, then nothing at all. You appear to dim, redden, and freeze, pinned to the horizon like an insect in amber. They could wait 1,000 years, 1,000,000,000, and from outside you would still be there, fading, never quite gone. But from your seat, none of this happens. You glance at your own watch, and it ticks along, perfectly normal. You cross the event horizon without fanfare. No wall, no barrier, often nothing at all to mark the most important line you will ever cross. By the time you realize it is behind you, it is already far too late. Both stories are correct. In Einstein's universe, there is no single now that everyone shares. Only the truth each observer carries with them. Gravity does not pull on all of you equally. Your feet, nearer the center, are pulled harder than your head. The difference is called a tidal force. On Earth, it is far too small to feel. Near a black hole, it becomes monstrous. Around a small stellar mass black hole, this stretching would tear you apart while you were still far outside, your body drawn into a thin stream of atoms. The physicist who named this fate had a grim sense of humor. He called it spaghettification, but you chose a supermassive giant, And this is exactly why. Because its enormous mass is spread across such a vast radius, the tidal force at the horizon is mild. You could cross it intact, body whole, watch you still ticking, mind still racing. The stretching comes later, deeper in, as you fall toward the center, and the difference in pull grows without limit. Gently at first, then with horrifying speed, you are drawn out into that long, thin thread. There is no surviving it, but you will have crossed the horizon as a living, thinking witness, the only human ever to see the inside of the universe's most forbidden region. Inside the horizon, the rules quietly rearrange themselves. Out here in everyday space, you can move forward or back, left or right, but you cannot avoid moving forward in time. Inside a black hole, the singularity takes over that role. It is not a place sitting at the center, waiting for you to arrive. It is a moment in your future, as unavoidable as next Tuesday. No matter which way you fire your rockets, every path leads forward to the same instant. You can no more steer away from the center than you can steer away from tomorrow. And what waits there, we genuinely do not know. Einstein's equations say density and gravity climb toward infinity, but infinity is physics admitting it has run out of language. At the singularity, general relativity, our theory of the very large collides with quantum mechanics, our theory of the very small, and the two flatly refuse to agree. To describe that final point, we would need a theory of quantum gravity that no one has yet written. So the honest answer to what lies at the center of a black hole is also the most thrilling sentence in science. Nobody knows. And yet, the black hole that swallowed you is not eternal. In 1974, Stephen Hawking showed that black holes are not perfectly black. At the very edge of the horizon, the strange rules of quantum mechanics allow a faint trickle of particles to escape, now called Hawking radiation. Atom by atom, across spans of time that defy comprehension, the black hole bleeds away its mass. A giant like Sagittarius A would take more than 10 to the 87th power years to fully evaporate, a number so vast that our universe, at 13.8 billion years old, has barely taken its first breath. But in the end, it will shrink, glow brighter, and vanish in a final flash, which leaves one last troubling question, the one that keeps physicists awake at night. When the black hole is gone, what happened to you? To the information that made you, every memory, every atom's arrangement? Quantum mechanics insists information can never truly be destroyed, and yet the black hole seems to erase it completely. This is the information paradox, and the thread that finally untangles it may be the same thread that stitches together the two broken halves of physics. You stepped forward expecting an ending. Instead, you found the edge of human knowledge. A black hole is where our finest theories go to be humbled, where time and space trade places, where two truths contradict each other and both hold, where the universe keeps its deepest secret just past a horizon that no signal can ever cross. We map the heavens with such confidence. But out there, in the dark between the stars, the cosmos is still keeping score, and there are places it simply does not let us follow. At least, not yet.